Hi ladies and gentlemen, this is Miss Skokin. We're in chapter 4, Triangle Congruence, and we're splitting this chapter in half, so we're starting with sections 1 through 4 first, and then we'll do the rest afterward. Starting out with section 4-1, Congruence and Transformations, and this is kind of going to be a flashback to some of the work we did with transformations earlier this year. So we're going to start out with the objectives: draw, identify, and describe transformations in the coordinate plane. Use properties of rigid motions to determine whether figures are congruent and to prove figures congruent. Dilation, isometry, and rigid transformation are our vocabulary for this section. We've got a warm-up, and we're going to start out with number 1. And what I'd like for you to do is try to figure these out on your own, but of course turn the video back on when you're done and check your work, check your answers. So I'll see you back in a minute when you turn the video back on. You can see on question 1, we've labeled, graphed and labeled the pre-image and the image. We see from the corresponding points A and A prime that the image is a translated version of the pre-image, 6 units to the right. That is a horizontal translation. Let's move on to number 2 now. Again, on number 2, we have graphed and labeled the pre-image and the image, and we can see that the orientation is completely opposite, unlike the one in number 1 where the orientation stayed the same but the position changed. In number 2, the orientation is upside down. The image is the upside down version of the pre-image, so we know that that has been a reflection in the vertical direction, and in this case it was reflected over the x-axis. Let's move forward. We know that a transformation is a change in the position, shape, or size of a figure. Some types of transformations are translations, which we used to call slides in middle school. Reflections, which we used to call flips. Rotations, which we used to call turns. We discussed these in class earlier this year, and one translation that we didn't discuss, or transformation that we did not discuss, was called a dilation. And a dilation keeps the same shape as the original, but it is either bigger or smaller. It's a change in the size. And in middle school, we used to refer to dilations as a stretch when the image was larger than the pre-image, or a shrink when the image was smaller than the pre-image. Now we're going to be talking about dilations in terms of the scale factor. And the scale factor is a number that we would multiply to the length of each of the segments of our object so that we know what the new length is going to be. We know that if we have a scale factor that is greater than 1, then the dilation is what we call a stretch. We know that all scale factors have to be larger than 0, so k has to be greater than 0, but sometimes k is going to be between 0 and 1. So it's a positive number, but a number smaller than 1. In that case, then the dilation is going to be a shrink, where the image is going to be smaller than the pre-image. One other thing that I want to point out before we move on, and that is the form of the mapping statement. You can see here that the mapping statement is going to be shown as a multiplication. So we're going to see that xy will map to, and it's going to be some number multiplied by x and the same number multiplied by y. So that's what our mapping statement for a dilation is going to look like. In example 1, we're going to be drawing and identifying the transformations that we draw. So the first thing that we're going to do is take a look at the M, or the mapping statement. The mapping statement is really telling us what type of a transformation is going to take place. And then we're going to draw or graph the pre-image, which we have the coordinates for those given to us. Then we're going to apply the mapping statement to the coordinates of the pre-image. That's going to result in the coordinates of the image, so we'll graph that, and then we'll identify the transformation. So let's start with question A. we see the mapping statement has x minus 4 for the new x coordinate and y plus 1 for the new y coordinate. That mapping statement tells us that we're going to be translating our pre-image to come up with the image. And it's going to move 4 units to the left, and it's going to move 1 unit up in the vertical direction. So let's get started by graphing the pre-image. We've got our pre-image graphed, and now we're going to apply the mapping statement to the coordinates of the pre-image. So point P was at 1, 3, and the mapping statement tells us that we're going to subtract 4 from the x-coordinate and add 1 to the y-coordinate. That means that P prime is going to be located at -3, 4. So at -3, 4, we map P prime, or we graph P prime. Now, one of the things that I want to draw your attention to is if we start out at P and we go 1, 2, 3, 4 units to the left and 1 unit up, we end up at point P prime, and that's exactly what the mapping statement told us to do. So next we've got to do the mapping for points Q prime and R prime, graph those, label our image, and then describe the transformation. So let's do that next. The last thing that we have to do for this question is write down what the transformation was and by how much. And it, of course, was a translation 4 units to the left and 1 unit up. Let's take a look at question B. Question B shows that the mapping statement has x mapping to x, so it doesn't change, but y maps to -y. And you may remember that that is the mapping statement for a reflection. So we have, once again, the points for the image, for the pre-image, A, B, and C. So let's go ahead and graph the points for the pre-image and label them appropriately. Once we've got the pre-image graphed and labeled, we're ready to start finding out what the coordinates for the image are. And we're going to keep the same x coordinate, and it's going to be the opposite y coordinate. So we're going to go through and determine those points, and then of course graph them. The image is now graphed and labeled, so now we just have to write down what type of a transformation it was, and just as we predicted, it is a reflection across the x-axis. Now we're ready to move on to question C. In question C, we take a look at what the mapping statement says, and we see that something weird has happened because the x and the y coordinate have reversed positions, and the new y coordinate, which is the old x coordinate, has gone negative. So a few different things happen here, but before we get ahead of ourselves, let's go ahead and graph the pre-image and label it, and then turn the video back on when you've done that. Pre-image is graphed and labeled, and now we're going to come up with the coordinates for the image. So for R prime, what was the y coordinate is going to become the x coordinate, so we'll put the 0 in that position. And then the new y coordinate is going to be the opposite of the old x coordinate. So our x coordinate is -3, that means our y coordinate is going to be 3. For E prime, we're going to have 3, 3 as the coordinates. For C prime, we're going to have 3, 1. And for T prime, we're going to have 0, 1. So let's graph those points now and create the image. So our pre-image was a rectangle and our image is a rectangle, but the orientation of the two rectangles is different. The pre-image is kind of standing up in the vertical direction, and in the image it's kind of laying down in the horizontal direction. And so let's take a look at what happened to the individual points. We can see that point T ended up at T prime, C ended up at C prime, E ended up at E prime, and R ended up at R prime. So when we take a look at this, we can see that what ended up happening was we had a rotation of 90 degrees in the clockwise direction. And the center of the rotation was the origin, or 0, 0. And now we know why that mapping statement looked so unusual. This is what a rotation mapping statement looks like. We see the x and the y coordinate switch positions, and one of the coordinates goes negative. Which one goes negative indicates to you the direction of the rotation. All right, now we're ready for question D. Looking at the mapping statement, we can see that the new x-coordinate is going to be 3 times the old x-coordinate, and the new y-coordinate is going to be 3 times the old y-coordinate. So this mapping statement actually tells us that we're going to have a figure with segments 3 times as long as the pre-image. So let's go ahead and pause the video, graph the pre-image, and then turn the video back on. Next, we're going to figure out what the coordinates of the image are. And of course, what we're going to do is multiply the x-coordinate and the y-coordinate by 3. So we're going to have -6, -3 for point K prime. L prime is going to be at 3, -3, and N prime is going to be at 3, -6. Let's graph those points. We can see that our image is another triangle, but it's a much larger triangle. And just a quick word about what happened here. We do have a center of dilation, or a point of dilation. And our scale factor was 3. We knew that because of the mapping statement. But our center of dilation, we can see, is going to be 0, 0, the origin. And if we go through the various points on the pre-image and keep going in that same direction, we get to the points on the image. So this is another way that you can see what your center of dilation is. That is it for example 1, so let's move on to example 2. Here are the different types of mapping statements that we see for the different types of transformations that we've been discussing. Okay, we have our new vocabulary. An isometry is a transformation that keeps the length, angle measurement, and area the same. So that means that the image will be congruent to the pre-image. A rigid transformation is another name for an isometry. Those two mean the same thing. And dilations, of course, are different. They are not isometries. They are not rigid transformations because they do change the size of the figure. It's going to either be a larger or a smaller figure than the pre-image was. And our box does the same thing about translations, reflections, and rotations. We know that the images are going to be congruent to the pre-images. Those are rigid transformations, also known as isometries, and dilations are not. Dilations have a scale factor not equal to -1, but it's got to be a positive number. In example 2, we want to determine whether figures are congruent. So we're going to be graphing the two polygons and determine if one is the rigid transformation of the other. So let's start out by graphing points A, B, and C, joining up those segments so we can see what that first figure is. Now let's graph points P, Q, and R and see what the change was between the two figures. We can see that all 3 segments of the two triangles are congruent. 1, 2, 3, 4, 1, 2, 3, 4. And this is, we can use the slope for to the right 1, up 2, to the right 1, up 2. And of course, then the diagonal between them is going to be the same. So these two triangles are congruent. Let's write that down. And the reason that they're congruent was because this type of transformation was a translation, and a translation is a rigid transformation, which means it's going to maintain the size and shape. So let's write that down now. In order to figure out the mapping statement, we have to figure out the two corresponding points. So A and P are actually corresponding. A was the first figure. So to get from A to P, we go 1 to the right. So that means it's an x minus 1. That's in the horizontal direction. In the vertical direction, we go 1, 2, 3 units down. So that's a minus 3 for the y. We have our mapping statement now. And it was a rigid transformation. Once we've got that one done, we can take a look at part B. And again, we're going to start by graphing points A, B, and C and seeing what kind of a figure we end up with. So now we have triangle ABC. Let's graph the second set of coordinates P, Q, and R and see what type of a transformation took place. Now that we've got both triangles graphed, we can see that they have the same shape, but they don't have the same size. So we know that this is a dilation, and we need to figure out what the scale factor is. So we know that these triangles are not congruent. Let's go ahead and write that down. So they're not congruent, and we need to figure out what the scale factor is so we can write down the mapping statement. In order to figure out exactly what the scale factor is, what we're going to do is we're going to take two of the corresponding, or one corresponding side from each of the triangles, so two corresponding sides, and we're going to pick an easy direction. If we can go either in the vertical direction or in the horizontal direction, of course, that's going to be easier. If we don't have that option, then we would need to use the distance formula to determine the length of two corresponding segments. In this case, though, we can use PQ and we can use AB, and we're going to create a scale factor K based on where we ended up compared to where we started out. So PQ was on the image, AB was on the pre-image, and the length of PQ is 1, 2, 3 units long. The length of AB is 2 units long, so we can either think of this as a scale factor of 3 over 2, or we know that that is 1.5 in decimal. So scale factor of 1.5, now we're ready to write our mapping statement. X comma y maps to 1.5x comma 1.5y. All right, done with that one. Now let's take a look at example 3. Applying transformations on example 3, we're going to prove that the polygons with the given vertices are congruent. And this gives us a hint. Look for the combinations of transformations. So that means there's more going on than just one transformation. So we're going to start out by graphing points A, B, and C and determining what that figure is. So let's start there. We've got triangle ABC and we've labeled it the pre-image. And now we're going to graph PQR, which we can presume is going to be another triangle. So go ahead and graph PQR. Now remember, that's our final image and there may be an intermediate transformation. But let's go ahead and graph PQR right now. We can see that the orientation of the pre-image is different. It is clearly there was a rotation that took place, because B started out at the bottom and now point Q, which corresponds to point B, is on the right hand side. So this definitely looks like it was a counterclockwise rotation of 90 degrees. However, we know that if that were the only transformation that had taken place, the image would not be in the location where it is, because we remember the mapping rule for a rotation 90 degrees counterclockwise. The x and the y coordinate switch, and the y coordinate, or the new x coordinate, becomes the negative of the old y coordinate. And so there would be a point A prime, B prime, and C prime that would give that intermediate location. So let's figure what those points are right now. A prime would be at -2, 1. B prime would be at -1, 2, and C prime would be at -2, 4. Let's graph those points and see where our figure ends up. Now we can see where the rotation only would have resulted. in. The triangle would have been where this green triangle is now, but obviously the image is PQR. That's the final location where our figure ended up, and so we need to figure out what other transformation took place. It has the same orientation, PQR does, as A prime, B prime, C prime. Because it has the same orientation, we already know it was a translation. Now we just have to figure out by how much. So our point P ended up at -3, -2. So what happened? It looks like our mapping statement should read x, y mapped to -y, x, which of course became our new x and y, and that mapped to, and what happened? We started out with x and y, and it looks like we went, looking at corresponding points like C prime and R, 1, 2, 3 down in the y direction, and 1 to the left in the x direction. So we have our mapping statements. We have two of them, of course, because two different transformations took place, but both of them were rigid transformations, so these figures, our preimage and our image, are the same size. And that means that our two triangles, triangle ABC, is congruent to triangle PQR. One last comment about these transformations. You can see that we did two transformations in a row. That is going to continue to take place. It's not going to be unusual, but what we need to remember is order matters. If we reverse the order of two different transformations, we're not going to necessarily end up in the same place. So we need to be very conscious of this, especially when we look at transformations in Algebra 2 using function notation. All right, that's it for now. The next page is your homework assignment. So I will see you back in class or see you back for section 4.2. Is your beginning of your homework questions. So you'll be working on those.